Organic chemistry. Okay, I know. Just hearing those words might give you some not-so-fond flashbacks to high school. But what if I told you it's not just about drawing complicated diagrams? What if I told you it's the secret science behind, well, almost everything that makes our modern lives modern? I mean, just look around you, right now. That water bottle sitting on your desk? The case protecting your phone? You know, the fuel that gets you from point A to point B? Yep, even the aspirin you might have in your medicine cabinet, all of them, every single one, is a product of organic chemistry. So what's the deal? What is the common thread that ties together plastics, fuels, and even life-saving medicines?
The answer, believe it or not, is actually pretty simple. It all comes down to the chemistry of one incredible, super versatile element, carbon.
That's right. You could honestly say that we're living in the carbon age. So today, we're going to break down the single most important building block of our world. Just how important is carbon? Well, get a load of this number, 20 million. That's roughly how many organic or carbon-based compounds we know of. It completely and utterly dwarfs everything else in chemistry. The difference is just staggering when you see it side by side. Organic chemistry, that's the 20 million compounds, all built around a carbon backbone, usually held together by what we call covalent bonds. Inorganic chemistry is literally everything else, all the other elements in the periodic table, and that only adds up to about 400,000 compounds. It just goes to show you carbon is a special, special element. So that begs the question, right? What makes this one element so special? Why is carbon the ultimate builder of the molecular world? Well, it really boils down to three simple but amazing superpowers. First, a single carbon atom can form 4 incredibly strong bonds. Chemists have a fancy word for this, tetravalent. Second, it has this amazing ability to link up with other carbon atoms, forming these long, super stable chains. And third, these chains aren't just straight lines. They can bend and connect to form rings and all sorts of complex three-dimensional shapes. It's basically the perfect molecular Lego piece. So, where does this building process begin? Well, it all starts with the simplest family of carbon compounds you can imagine, the hydrocarbons, and we're going to meet a group called the alkanes. Okay, so alkanes are the absolute basics. They're made of only 2 things, carbon and hydrogen, all connected by single bonds. They're also sometimes called paraffins, which actually means inert or less reactive. And that's because those single bonds are just so stable and strong. This family starts out really small. You've got methane, CH4, the simplest one possible. Add 1 more carbon and a few hydrogens, and boom, you get ethane, C2H6. Add another, and now you've got propane, C3H8. You see the pattern here, right? Each one is just a little link longer than the one before it. We call this a homologous series. All right, so building simple chains is pretty cool. But here's where it gets really interesting. What happens when you have the exact same number of atoms, but you connect them in a totally different way? And this is where that Lego analogy we talked about just clicks into place. You can take the exact same handful of blocks and build completely different things, right? Well, in chemistry, that's a fundamental concept called isomers. These are different compounds that have the exact same molecular formula, the same parts list, if you will, but a totally different structure. This simple idea, this ability to rearrange the pieces, is the secret to how carbon can create such an absolutely immense variety of molecules. Okay, so we've gone from a single atom to simple little chains, but how do we make the leap from there to, the plastics and all the other materials that are literally all around us? How does carbon create this endless variety? The answer is a really cool process called polymerization. All that means is it's a chemical reaction that takes a whole bunch of small, individual molecules, we call those monomers, and links them all together into one giant chain-like molecule, which we call a polymer. Let's make this real with something we all know, plastic. So you start with a massive number of tiny little ethylene molecules. Then a chemical reaction comes along and acts like molecular glue, linking them all together end to end to end. And the result? A long, stable polymer chain that we all know as polyethylene. Simple as that. And this simple process of linking carbon chains gives us the world we recognize. Polyethylene for plastic bags and bottles, PVC for pipes, polystyrene for that foam packaging, even the Teflon that makes our pans non-stick. They are all just different kinds of massive molecules built on a carbon backbone. So let's just zoom out for a second here. We've kind of taken a journey from this invisible world of a single atom all the way up to the stuff you interact with in your daily life. This entire story, this whole world of materials, it all starts with one simple fact. A single carbon atom can form 4 strong bonds. That one ability allows it to build simple little chains, like the propane gas in your grill, which can then be linked together into enormous polymer chains, like the Teflon on your frying pan. Carbon is truly the quiet architect of our modern world. So the same fundamental chemistry that gave us plastics and fuels and medicines, it's all still right there, waiting. It built the world we live in today. And that really only leaves one question. What are we going to build with it next?